Okay, I think we can start officially. Welcome back, everyone. So today we're finishing off section 5.2, and then we're going to make some headway into section 5.3. Pretty much all we'll be doing is loads and loads of computations, lots of antiderivatives. And our assignment number 12 is just going to be these two sections here. Now this looks like a lot, but it's not like this was some section from section 4.8 on optimization. These are like doing derivatives. They're going to be pretty fast kind of problems. These are the longer ones, so not as many in this set. And just a reminder also about assignment number 11, this one had a due date that was put in as an extension. But we also mentioned an extra credit opportunity about the late homework. I haven't officially wrote it out yet, but I'll have that posted pretty soon. I'm going to put it right under here. Well, any questions, folks, about any of those announcements before we get started? Okay, well, we're up to our really big target in chapter 5, Fundamental Theorem of Calculus. But before we get to that, it's really important to talk about properties our definite integral might have. So here's a big long list of those kinds of properties. But now when you look at this list, there's a lot of interesting things that are happening here. Like, for example, on this one, or no, this one right here, property number 5, this might feel really very familiar. So might say property number 4. Well, really, those are the only two I was thinking of. But the familiarity with these kinds of properties are, say, for example, if you're taking the derivative with respect to x of c times f of x. A constant times a function, if you take the derivative, that's the same as the constant times the derivative of the function, df dx. What this is saying up here is if you integrate a constant times a function, you can just take the constant and multiply it by the integral of the function, and you have the same result. It's kind of curious how that ties together. The same kind of deal here. We've used properties that say, for example, derivative with respect to x of f of x plus g of x is the derivative of f with respect to x plus the derivative of g with respect to x. So this property is saying that the derivative of a sum is the sum of those derivatives. And this property is saying the integral of a sum or a difference is the sum or difference of the respective integrals. So all these properties, they keep on coming back. Yeah, go ahead. The a and b? Yeah, the whole symbol here is the start and the dx would be the end. Yes. Other questions so far? Okay. Well, if you're curious where all these things are coming from, the integral formulas, the derivative formulas, it really came from way, way back in the day, from this section up here. Every single property was really the limit laws. So the limit laws were telling us things along the lines of the limit of a constant times a function is the constant times the limit of the function. That ties directly into our derivatives. And the reason that is because the derivatives are limits. Derivatives are limits, continuity are limits, and the reason it ties into integrals is because an integral is also a limit. So every property that we define through a limit, that's all the properties of calculus, take advantage of the limit laws. And that's why the formulas start to become so familiar. Every one of these can be just finely tuned to either your derivative or your integral because they're both just really fancy limits, admittedly, but they're still just limits. So that is telling us where those two are coming from. And part of our goal is to see what the rest of the formulas are doing altogether. I don't have a very interesting problem for part 6 right here, but we have some interesting information for all the others that we'll give a try. Any other questions so far, folks, before we try out some of these properties? Okay, so example 6 sounds pretty nasty. It's telling us to directly evaluate that integral. We have to put a number to it, and we're not approximating using a midpoint rule or otherwise. We're finding it out exactly. And here's how we could approach it. A definite integral from 0 to 2 with a 5x plus 1. This one's not terrible to calculate because the definite integral is going to represent a signed area under this curve. And we can even make this nicer. You don't have to settle for 5x plus 1. Let's apply property number 4 on this thing. You can break this up if you like and say integrate from 0 to 2 of 5x dx, then add to it the definite integral from 0 to 2 of the function 1 dx. That looks a little bit weird having just a 1 there, but it's a valid way to write the integral. We're integrating a constant function 1. Over here, we're integrating a linear function 5x, and we can definitely integrate those because these are just straight line segments. We can find the areas by using ordinary area formulas. So let's break it up into 2 problems now. Let's do 2 really fast graphs just to visualize. On the first one, we're integrating from 0 to 2. Well, both of them we are, so I'll go from 0 to 2. Plug in 0 and 5x, and we take on a value of 0. If you plug in 2 and 5x, you take on a value of 10. And so this is the really fast graph of 5x on the domain 0 to 2. We can put a boundary here, and now there's definitely a finite area. It's 1/2 base times height. The base is the distance from 0 to 2 along that direction, and the height would be the distance from 0 to 10, so it's at a height 10. As the whole thing just turns out to 10. That means the first part is done. That definite integral represents area. This curve was totally above the x-axis, so it's a positive area. And we'll write this in as 10. Then we'll just do it again, and the next step is even faster. But does that make sense to folks at the moment? Okay, let's try again with the next function. This one is the constant function, always equal to 1 for all values of x. But the values we'll take are, again, just between 0 and 2. So go from 0 to 2. Here's our function. It's at height 1. Goes from here, ends right here. And we need that area. That's just going to be base times height. So area is going to be 2 by 1. For area of 2, which we can plug in back up here, coming from that second definite integral. So the whole thing evaluates to 12. That's not terrible, but having to use our area arguments like this definitely has its limits. Some curves we don't have great areas under. If it ever did something like this, for example, that's going to be a hard one to find the area under the curve of. I don't have an area formula for that specific kind of curve whatsoever. But anything that involves straight line segments, these problems don't necessarily need the fancy methods. You could, from brute force and first principles, get the value out. Any questions about that one so far? Okay, so we are now integrating at this point, but the way we're integrating is kind of like when we differentiate before the differentiation rules. Sometimes when we said y equals 3x plus 2, before we had the power rule, we said, well, y prime should be equal to 3 because the derivative of y is equal to the slope of the tangent line. It just happens to be linear, so they gave us a slope. It's 3. That's kind of like how we did it right here. We want to extend all of these methods, just like we weren't satisfied with 3x plus 2 when we did that problem. But let's try out another one just to get a feel for this. This is the weird one. We're integrating from 0 to 2, 5x plus 1. Now, there's a formula for that. It's this right up here. If you have limits of integration that go a to b, and if for some reason you ever want to switch them, you can. We've mentioned before that it doesn't have to go the lower number to a higher number. That's just what's typical. If you switch your limits of integration, all you have to do is put in an extra negative sign right here. And there's a definite reason for why all that works. Let's put just a really quick sketch on that reasoning there. If you write out the definite integral from a to b, f of x dx, you're looking at the limit as n goes to infinity, summation as I goes from 1 to n, of f of x times your delta x. But here delta x is going to be b minus a divided by n. Now imagine what you would do if you swapped that delta x. Set delta x to, let's set negative delta x to a minus b over n. Now we're swapping the limits of integration. I factored a negative sign out of the numerator to get that negative delta x. And we could say here, if that's our delta x, then the limit as n goes to infinity, summation as I goes from 1 to n, using this delta x, we'll still put an f of x here. Delta x can go right here, but now I have that negative sign. The negative sign can pass through summation. It's just factoring out the greatest common factor through all those pluses. -1 is a constant, so it passes through the limit and merges right here. Because we have a minus b right here, we'll say that this is going to be a definite integral from a to b of f of x dx, and that negative sign from right here just carries right over. So really the effect of switching the limits of integration, that's just switching around your delta x and factoring out a negative sign. Just a weird consequence of the algebra of the delta x in this process. But it turns into a formula that's sometimes kind of valuable to have. So back to our problem. Sorry, let me copy some of this down. Back to our problem below. We want to evaluate a definite integral from 2 to 0. You don't necessarily have to switch that order there when we're in section 5.3, but in this section, it's a really good idea. That's a confusing process. So let's start out by writing the definite integral from 2 to 0 of 5x plus 1 dx is just as good as, let's throw in a negative sign in front of the whole integral, swap the limits of integration, so now it's 0 to 2, of 5x plus 1. So that's the whole use of formula number 1 right there. And the fact that we used it means our problem is easier to do. We've already integrated 5x plus 1. It came out to a 12. So this thing now just turns into -12 altogether. Any questions with that one there, folks? Yeah. Yeah, we would think of it below the x-axis only if we thought of this negative sign, which can go inside the integral, going right here. So now we're thinking of this process when you're switching the order of integration, you are truly negating the function. It's below the x-axis now. Does that make sense thinking in those terms? It can, yes. That's the property. Oh, I'm up here now. That's the property right here. Think of this c as playing the role of the -1. If you have a constant, it can go inside the integral or outside, just wherever is more convenient. Exactly, yes. Other questions so far? Okay, so that's a couple of really fast integrals, only because the functions were special, and the second problem was rigged to line up with the first problem. And so is the next one. Example number 8 says, evaluate this integral. We're going to go from 0 to 2 of 100 times 5x plus 1. But all we need to do this time is take a constant that's a bit of a nuisance. And the big takeaway from this problem is sometimes it's very valuable to take out a constant that allows you to focus on the integrand and go and worry about how to integrate the thing inside. So the first thing to do on this problem would be integrate from 0 to 2 of 100 5x plus 1. But do that by taking the 100 and let it come outside the integral. Just like with derivatives, the integral of a constant, you can just pull the constant out and place it right here. Then 5x plus 1 goes inside. It's still integrating from 0 to 2, so it still needs that symbol and the integral sign. So now it's 100 times our integral from 5x plus 1. That was 12 up above, so it's 100 by 12. Equaling 1,200. So that's our result on this one here. Any questions, folks, with those kind of fast problems with the concepts of those properties? Okay, well, that's doing some really quick integrals that we can calculate in a fast way without having to cite a convoluted limit. But eventually we are going to have to deal with trying to calculate more interesting problems than this one. And so that's what we'll be doing in the next section, dealing with the fundamental theorem of calculus. The fundamental theorem of calculus has 2 parts, though, which is kind of confusing. The first part is definitely useful, but it's something that gets used in some more advanced classes. It could be used in probability if you're dealing with normal distributions, for example. And here's a problem that is very much in the spirit of the fundamental theorem of calculus part 1, in the sense that these are the functions that you deal with in the fundamental theorem of calculus, and same with probabilities as well. So this is a function f of x, which integrates from 2 to x, f of t dt, where f is the function whose graph is given, so here's f of t down below. And I added this as a quick edit. The original document, if you printed it out, only went to f of 4. Then I looked at the problem again today, and it seems like it's a funner problem if you put it all the way to f of 5. I think this is a better experience. So sorry for that. That's another quick edit on these notes. But before we go to solve this problem, let's take another look at f of x. That's a strange function. So f of x is the signed area under the graph of y equals f of x. Oh, that's not an x, is it? Y equals f of t from 0. So we're always going to start right at 0. That's what's in. Oh, no, hang on. It's from 2 to x. I think that's kind of an unnecessary complication. Let's change this one as well. Sorry about that, folks. I think this one would make a little bit more sense if we start at 0 right here. So 2 quick edits on the problem. There's a 0 on the lower bound of this thing and an f of 5. So that 0 is going to line up from here to here, from 0 to x. Maybe let's start over again. We threw in a couple edits there. So f of x says integrate from 0 to x, f of t dt. So that means it'll be the sign area under this graph with those changes put in. So the question they're asking us then is, which of the following values is largest and which is going to be smallest? If we take a look at f of 0, then f of 0 is kind of a confusing question, right? It's saying integrate from 0, that's our lower bound we put in red, up to the value of x, but x is 0 here, of f of t dt. So definite integral from 0 to 0, that can be done. There's no one stopping us. This is a real problem we can get a real number to. Any volunteers for what the value should be? I agree, it ought to be exactly 0. This still represents the area under the curve, but we're now asking for an area of a line segment. It has no width to assign an area to. This is automatically area 0. So that helps us out to start this off. And the concept that we're using for that one is this one right here. If you do a definite integral from the same lower bound to the same upper bound, you're trying to find the area of a line segment, which is automatically area 0. So f of 0 is going to come out to 0. If we take f of 1, then we have this much area in the problem. All I can say directly about that is, well, f of 1 then is certainly bigger than 0. We take a look at f of 2, it's going to be all of this area. So f of 2 is bigger than 0, but it's also bigger than f of 1. Let's maybe put that in a more cohesive way. F of 1 is bigger than 0, which is less of f of 2. And at this stage, it looks like f of 2 would be the largest. The moment you go to f of 3, the visualization for f of 3 would be, you're taking the area in black, then the area in green, which is negative, it's going to be smaller than f of 2. So this is less than f of 2. It looks like f of 2 would be the largest because that's where we stop accumulating positive area. Go beyond that, the curve dips below the x-axis. All this area is now negative. So we can make a statement right here. F of 2 is the largest. Does that make sense so far to folks on getting that largest value? Okay. The trick to this kind of problem is just think about the areas, but think of them as the signed areas, like we mentioned up here. Whenever you have Anything above the x-axis, that's your positive area. Area below x-axis is your negative one. Now at this stage, we take a look at, say, f at 4 next. We'll have positive area right out here, negative area out here, and it looks like it almost balances. I would say that f of 4 is approximately 0. It might have been designed to be exactly 0, but that's hard to tell visually. That's why I included one more, f of 5. If you do f of 5, this one is visualized by going, takes all that positive area to start, but then we take up all this negative area. And I would say that f of 5, this one looks like it's truly negative this time. It does look like there's more negative area than positive area. Does that look about right to everyone in class? Okay, so since the blue area is larger, we'll say f of 5 is negative. That means it's the only negative value on the papers at the moment. So we can go back to f of 5 right here and assert this is the smallest. So that's our really bizarre function. These functions are, again, pretty powerful tools. One thing we're going to find out the more calculus we do is not every function has a nice antiderivative, but every function you can find an antiderivative in this form. That's what the fundamental theorem of calculus part 1 is talking about. That form isn't always useful, but sometimes places like differential equations, we have to use that kind of antiderivative. There's no other thing available to us. But we did it, folks. That's the end of these notes. We just had a little bit to tie off before we go to the next section. Any questions or comments before we change to section 5.3? Yeah.
In the book, they go over sums of powers.
Yeah, I think I skipped the sums of powers only because we weren't doing these limits right here directly. We were only just expressing them as, say, a limit like this, but we weren't trying to endeavor to actually calculate the amount. But you're talking about, just to make sure if I'm on the right track, stuff like summation I goes from 1 to n of something like I, right?
Yeah,
yeah, all those would be used to try to attempt to evaluate these kinds of limits. And the book does do a couple of them. They can, I think they integrated y equals x cubed or something using those formulas. They had to use the I formula, the I squared, and the I cubed formula.
And so what they do is that they find another way of finding the area.
It'd be the way to find the area in the hardest possible way before using the fundamental theorem of calculus.
Is it useful for other classes to like really understand them?
I'd say it would be useful, but if you're using those formulas directly, it'd be kind of strange, since if you had to integrate something, you're more likely to use the fundamental theorem of calculus. You would need those tools if you're taking, like, say, an elementary analysis class and you're proving certain results using those ideas. So I'd say it's definitely still important material, but our course isn't going to hit on those directly. Yep, you betcha. Other questions so far? Okay, let's go off then to that next section. Once that finishes saving. Sometimes these take a while to save. And so finally, we're in section 5.3, the fundamental theorem of calculus. Now, part 1 is the more theoretical one. It's based off the function that we were just taking a look at, a function that gives you an area from a up to x. So fundamental theorem of calculus part 1 says, if you have a continuous function on a closed interval, that's really good stuff, then that function is automatically integrable. That means you can specify a new function g by saying g of x is the integral of f of t from a to x. Now, the function f didn't have to have variable t, but there is a conflict of notation right here. We have to use x because the variable for g is x goes there, but if x goes there, if that was thought of as a f of x, we change that variable to something else. We think of that as a dummy variable. It's going to have the same meaning whether you put in f of a dA, f of z dz, but if there's a conflict with the limit of notation, we wouldn't put f of x dx, we would do f of t dt just to be a little bit more clear. Not necessarily that it's wrong if you put f of x dx, it just has a conflict. So that's our function that we're really interested about. Its domain is the same as the original domain of the function f, the integrand inside. But the fundamental theorem of calculus says these functions are very, very direct to differentiate. It's differentiable, and the derivative of that function, which is complicated, is simply the integrand. And we put in the variable which was original to it, x itself. Visualizing it in Leibniz makes it more striking. It's saying the derivative with respect to x of the integral from a to x is just f of x. In this way, we can think of integration and differentiation as being completely inverted processes. Well, through at least this formula right here. So that's kind of a wild problem. Again, the major use for this is if you have a complicated function, like say, for example, this thing, y equals e to the power of x cubed. These functions are really, really nasty. This has no closed form antiderivative. And what I mean by that is, well, there is an antiderivative, but it is impossible for me to write it down as something like f of x equals, I can't write down a formula for this thing using ordinary functions like x, sine, cosines, that kind of stuff, and putting them together with multiplications, divisions, and so on. We need something else on this thing. Calculus 2 is going to show one way to do this through power series, but already there is an antiderivative that's valuable. This is useful in differential equations. It doesn't have a closed form antiderivative. However, f of x, which is a definite integral from, now this a can be any constant whatsoever. The function I'm dealing with has the entire real number line as a domain. And so we can think of this as, let's say, domain 0 to maybe 5. It has domain all real numbers, but we need to specify some domain on this thing. So we'll integrate from 0 to x, e to the t cubed dt, and that thing right there is an antiderivative of y equals e to the x cubed. I did make one mistake on my antiderivative. It's the common mistake I usually mess up right here. I want to put a constant c to make it an arbitrary antiderivative. So this is the most general one possible. And the reason it works out as an antiderivative is, if you differentiate this function, fundamental theorem of calculus part 1 says, derivative of f of x is the integrand, lowercase f of x, e to the x squared is what we would pick up. So fundamental theorem of calculus, I think the best way to think about it is it's applying us an immediate antiderivative. Well, any questions about it so far? Okay, this topic is kind of a strange topic in all honesty. It's a great topic that goes along with other material later on, and so it's something that your classes are eventually going to wrap back to. All we're doing with this concept is we're just differentiating it and getting familiar with the differentiation process. So let's try it out with a few quick examples. I have a couple here that matches up with the homework. Let's go with a definite integral from 3 to x of, oh, I need to specify the function to start. Give me one moment. We should say g of x, that's the function we're defining, is a definite integral from 0 to x of square root t squared plus 4 dt. So there's our problem. And the solution is kind of nice in a way. All I would probably write out is g prime of x. That means we're differentiating with respect to x. The definite integral from 0 to x of root t squared plus 4 dt for the action of the derivative with respect to x. And this very, very specific function is to give you f of x is what it's telling us. F of x was the integrand, so we go over here, change the variable from t to x, only because the original function was a variable x, and our answer is root x squared plus 4. And then we stop. That's the whole process on this thing. Kind of a weird formula. Any questions about that so far? Okay, so calculating with these is not so bad, but we have to be really, really careful. X has to be the upper limit of integration. If we take that away, we have to correct this thing to force it to be the upper limit of integration, and then we're in good shape. The thing below has to be any number in the domain of the original function. By the original function, we mean the integrand a has to be a value of the integrand f of t. So we're okay with any number here that matches up with the function. And for a second one, let's try for part B. Let's integrate a more problematic function. This is g of x equals a definite integral from x to 0 of sine h e to the t dt. I have a bad habit of putting x's here, so that's never a good thing to do. I had to control z that a little bit. So if that's our function, then again, this is pretty fast, but this one is tricky. We can't directly integrate it right here. We have to fix it first. Anyone see what the way we could fix this to make it work?
The negative, the x on top and the negative in front.
Exactly. We can flip this around and get, to start, g of x. So negative in front. Integrate from 0 to x of hyperbolic sine h e to the t dt. So now we're in great shape. That's our new g of x function. Does that make sense on that step? Yeah, go ahead.
Why does that mean it's why can't it?
Well, the way this is proved right here, it has to be x above. The only reason for that is, yeah, the theorem right here directly requires that x.
Okay.
Other questions about that so far? Okay, so essentially all we're doing is we used somewhere over here. There it is. This property, property number 1, we swapped b and a, put them in those corresponding locations, just threw an extra negative sign in front. And now that's our g of x function right there. So now we can differentiate it, g prime of x. I think this step is kind of fun to write because, again, it's emphasizing the way differential calculus and integral calculus are connected, but you don't even have to write that step. The derivative of this is going to be automatically a negative sign, hyperbolic sign of e to the x now, and then done. That's the whole thing to that process. So fundamental theorem of calculus part 1 is kind of nice once we get used to it. There's not a lot to really calculate. In fact, our part C is going to be our attempt to make it as nasty as possible. This is the nastiest kind of question you could ever see for this problem. There's other problems that are slightly worse, but I think they're really kind of reaching and being contortionistic just to make a confusing problem. This one is more realistic. So part C was going to be the definite integral, or excuse me, is going to be a function z of x. Always forget to specify the function, which is a definite integral from 5 to x cubed of t natural log t dt. So that's our problem to start. The thing that varies is in the upper limit of integration, so we don't have to swap them. We're going to leave the function directly in this format. But there is something different about this problem. Has anyone spotted the extra complication about the z of x function? Exactly. It's not just x going inside. This is really a function composition now. So when we look at this one, the moment you see that, this is now a chain rule problem. This is the inner function we handle second. And the entire integral function, it's kind of hard to know what to point to because, I mean, The integral sign and the dt is the integral function, including the integrand that goes in. I'll just use a bracket. This is the outer function that we do first. So the process will say, when we differentiate this using the fundamental theorem, first, we'll wipe out the integral sign, we'll differentiate in the normal way, but then we'll evolve the x cubed function. So let's write out this one really carefully. Z prime at x is going to be, first, let's do the outer function. Fundamental theorem of calculus says, take this right here, we're going to input something, and that's going to be the function. But we want a bunch of placeholders this time. We don't want to write down t at all. So we'll put in a placeholder for t, natural log of another placeholder. Then we go to step 2 here and multiply by the derivative of inner function. So times the derivative of something. Now we have a whole bunch of placeholders, and up here above, we had a placeholder here too, but we just threw in x, right where e to the t was. Here we're throwing in x cubed, right where t was. It goes here, here, and here. So out of the nowhere, there's a chain rule. So that's the next thing to watch out for in the homework. Make sure your upper limit involves x, but if it's more than x, if it's sine x, cosine x, x cubed, it'll be a chain rule in this kind of way. So our next step will be to write out x cubed, natural log x cubed. We take this derivative, so that's our step 2 in the chain rule process. It's a 3x squared. So now this whole thing can become 3. We have x cubed and x squared, so they combine to x power 5 times the natural log of x cubed. That 3 looks a little bit weird. Let's fix that thing. So that's pretty much it. I guess you could do more to this. You can take the 3, move it out in front, and get 9x power 5 times natural log x, but I think it's a good stopping point. I don't know if there's any cost to try to simplify further. But we did it, folks. That's the first part of the fundamental theorem of calculus. Any questions at all about it? Yeah. Well, if it was just, say, an x right here, then z prime of t would have been, we take the function right here, we throw in x, natural log x, and then that would have been the answer if it was like just an x here. But if you put an x cubed, it still has to go somewhere. It goes into those same locations. And then you have to multiply by the derivative of it through the chain rule. So essentially, whatever's here goes into the variable t inside. But then if it's more than x, you also have to differentiate it. Does that make sense with that question there?
Yeah.
Awesome. Was there a question up here? Yeah.
Well, so you combine x cubed times 3x squared to get 3x squared?
Yes. Yeah. Yeah, I pretty much put the 3 way out front and just added up the exponent 3 and power 2 to come up with power 5. Other questions at the moment? Yeah.
So they kind of like inverses from each other, but then that x cubed is not inside the angle, and that's why you can derivative like normal dot.
Yeah, this is an input to the function right at this location. But the moment your input to the function is anything other than x, it implies a chain rule right exactly here. Exactly. Other questions about that? It definitely just looks weird. I think that's one of the things that's kind of tricky about this thing. We're used to the input to the function not being part of an integral sign, but it definitely can be for these kinds of functions. So the moment you switch out to anything here, you've got a chain rule scenario to navigate through. I think there's probably one of those on the actual homework as well. Any other questions at the moment, folks? Okay, thanks for all those questions. They're right questions to ask about this strange new material we're in. And like I mentioned before, fundamental theorem of calculus 1 is a pretty cool topic, but it's a little bit more esoteric. It's one of those topics where you might see like one question on a final exam, but it won't be super emphasized. The thing that will be emphasized is definitely this right here. This is our main technique of chapter 5, fundamental theorem of calculus part 2. In fact, if you say fundamental theorem of calculus, irregardless of which book you're looking in, most people are thinking of this theorem right here specifically. This one's proved by using the extreme value theorem. Extreme value theorem just needed a continuous function on a closed interval, and we have that. They also had to use the mean value theorem, and putting those all together gives this massive result. So this is one of the results that pretty much made Leibniz and Newton the founders of calculus. They independently discovered this fact right here, which is a pretty deep fact about mathematics. It's saying if you do a definite integral, that's signed area of a function f of x, you just need any antiderivative, evaluate it at the boundary points, the upper limit minus lower limit, and you are done. That is always the correct signed area each and every time. It means you never even had to do these limits. Well, you do if we don't know the process, and people did have to calculate these things with strange methods using brute force. These were very, very hard problems that took people decades of their lives to give good answers to. But here, we'll solve this problem immediately and directly. We're going to go from 0 to pi over 2. 3 pi over 2. We're integrating sine x dx. And the process says, first find any antiderivative. Let's call this part A to start. I'll leave black to be the actual question, and any other color means that's us solving the problem. So here's the first thing we need to do. We need to find f, the antiderivative of the integrand, lowercase f. Anyone happen to see what that antiderivative should be? It feels weird because we're not using like a lowercase f of x to indicate the sine x or writing out an uppercase f of x, but we're still doing the same kind of antiderivatives exactly as we did in section 4.9 on antiderivatives. And the methods we used were, we pretty much did this. We saw a trig function, we need to find information on how to do the derivative of a trig function. So we scoot all the way down to, say, section 3.3. Sorry, say again? Exactly, derivative of negative cosine becomes sine, so that's the correct antiderivative. We can scroll down to, say, this table right here. Let's check our problem. If we have a sine x, we go to where we see sine x as an output to the derivative. There's an extra negative, so we're going to throw that negative over here. Negative cosine x, just like you said. So antiderivative is negative cosine x. And we found our antiderivative f. Now, the way these are written as a formula here is different from the way people typically write these out in the solution as a process on paper. Even when you look at the formulas in your own book versus how they're calculated, this is never actually written. That's kind of confusing. What's written instead of that is this. F of b minus f of a is the same thing as saying f of x with an evaluation bar from a to b. We use evaluation bars like that whenever we're evaluating a derivative in Leibniz notation. But now this one has an extra decoration. It's going to be an evaluation at b to start, so that's the f of b, and then an evaluation at a to end, so that's the f of a. So that the moment you find an antiderivative, the next thing you would want to write is this. Evaluate from 0 to 3 pi divided by 2. So that's our evaluation. Note there's a negative sign right here that we have to be very, very careful with when we do that. And sometimes the best protection against too many negative signs in your problem is to factor away that negative sign. We can associate like this. Do the evaluation inside and then just multiply the whole result by the negative. It seems like it's such a small step, but it truly helps to keep us unjumbled for dealing with that extra negative sign. So now our next step is going to be, the negative is still right there. Then we take the upper limit, 3 pi over 2, just plug it into your antiderivative. It's now cosine at 3 pi divided by 2. Then This negative has to be written in no matter how you did the problem. So here's that negative connecting in. So we're done with the upper limit. We've got our negative sign. Then just throw in the lower limit of 0. It goes inside cosine 0. So cosine 0 here. And that's the minus f of a part. All that's left to do is just simplify this all together. Now we could get a really quick trig wheel here, or trigonometric circle. 3 pi over 2 is way down here. The cosine value would be the x coordinate in that location, which is a 0. We have a 0 right here, and this is now turning into negative 0 minus cosine at 0 places us here. The x coordinate is 1, so minus 1. And that whole thing simplifies to exactly 1. So this is the exact signed area under the curve of sine x, going from 0 to 3 pi over 2. And you know what? We got pretty close then. We got to 1.02, so we're only off by about 200ths in our estimation, which makes sense. This took a lot of work to get that computation, but it was only good for that much accuracy, unfortunately. Here, with very, very minimal effort, this took 2 minutes as opposed to like 20 minutes. We found area is exactly 1, and that's the whole story. Any questions about that so far? Okay, and again, these things feel like kind of parlor tricks. So what, we've got an area, it's not always easy to see why that's so interesting, but massive amounts of things from physics, engineering, chemistry, and so on, you can name lots of the disciplines. Interesting concepts are areas, whether they be distances or energy or something along those lines. They can be visualized as areas, and they're analyzed by doing these kinds of integrals right here. So definite integral always gives a number, and we just need the antiderivative to make that whole thing happen. Our goal is just to practice a whole bunch of these, but any questions, folks, with that first one? Okay, let's try out another one for our part B. Let's do another throwback, and we'll do some harder ones as we go. Let's do, oh, that's not uploaded yet, but let's do this one right here. 0 to 2 of 5x plus 1. That's a decent problem to start off with this theorem. So we want the definite integral from 0 to 2 of 5x plus 1. Let me move that off there. Dx. So first thing, we need an antiderivative of 5x plus 1, but that's not so bad. We did these quite a bit in section 4.9, finding antiderivatives. We start with this x. It has a power 1, so that power has to increase to a power of 2. We can write it in the 5. Now x to 1 power higher, power 2. Then divide by that power. It's 5 halves x squared. And don't forget, every time you do this, eyeball it or write down on the margin. If you were to differentiate 5 halves x squared, you would get 5 halves times 2 times x power 1, and it would turn into 5x after simplifying, which tells us we do have the right antiderivative. So double check your answers as you go, and that's a really great way to make sure you're accurate at each step. Then let's go off to the next one. Any volunteers for the antiderivative of just 1? It would be x, absolutely. So plus x right here. Now we have a multiple terms. There's no great trick for factoring out a constant like we did here. We just have to take the whole entire thing, evaluate it from the lower limit that was given at 0, and the upper limit of 2. So that's where our problem settles. And now next step, really just a bunch of arithmetic. So let's go and write out these steps that we see here. You always start with the upper limit of integration. So think top down when you do this process. We'll turn into 5 halves. Throw in that 2 to the power 2. Then plus 2 here for x. So that settles our upper limit of integration. The negative sign is definitely easy to lose track of this on this thing. So let's put it here. I'll emphasize these as we go. And the reason the negative sign is nasty this time is this function that we're evaluating a second time at 0 comes as 2 terms. we're required this time to put in a parenthesis to see the negative distribute through correctly this time. So throw in that additional parenthesis. Back over here, 0 is going in. And 0 is always nice for this kind of function, right? It's just going to wipe out everything. But I'll write it in just to show the pattern. It's 5/2, 0 squared, plus 0. So this one's just about done. And hopefully this is the right answer, but if we look at it, I think we did have 5/2 times 2 squared in a certain form, plus a 2. Simplifying this, we have 5/2 times 4 plus 2. That would reduce to 10 plus 2, giving us a result of 12 altogether. And I believe that's what we got earlier when we were doing that same kind of process. So the area under this curve is 12. This function is positive, so this is ordinary area. There's no signed area here to subtract. So that's 2 problems down. Any questions with that so far, folks? Okay, let's try out a kind of a nasty one next. Part C. We want to do a definite integral from, let's make it be -2 to -1 of 1 over x. I would say this is probably one of the more trickier problems. We made a big deal out of this one. There is a problem with finding antiderivatives of things like 5x or 5x squared. There's exactly one exception. The antiderivative of this is not a power function at all. It turns into something else. Anyone happen to remember what it was? It turns into a natural logarithm. Good call. So this thing has antiderivative that goes natural log x. But we need our antiderivative to be as general as possible. And that's where this formula came into play. Natural log of absolute value of x. We truly need the absolute value this time because our limits of integration themselves are negative. Without that, this problem wouldn't have been defined. But in this antiderivative, we can now evaluate it from -2 to -1 and get a real answer out of this thing. The one thing that we couldn't have done is, I can't integrate this from -2 to, say, 5, because the function itself is not continuous at 0. So as long as you keep your domain of integration away from 0, this always has an answer. And this problem is, again, definitely worth mentioning as a formula. Here, where did my cursor go? So the formula, let's put maybe right over here, is that the antiderivative of f of x equals natural log, or excuse me, equals 1 over x, getting a little too many steps ahead there, is f of x equals the natural log of absolute value of x plus an arbitrary constant c. So that's a formula that we use right here, but it kind of begs a question already. When you write an antiderivative formula, you must put in the arbitrary constant of integration. Yet when we're doing the definite integrals, we definitely don't put that in at all. Anyone happen to know the reasoning behind that? It's kind of a strange thing that happens on this thing, but one thing to emphasize first is note that it says any antiderivative. The any there is important. It tells us we might as well take the simplest one. That's why we never put a constant of integration on cosine. We never put it on 5x plus 1 when we found its antiderivative. We definitely didn't on this one. But if we did, here's how it would have looked. It would have been natural log, absolute value of x, plus a constant. If you evaluate that from -2 to -1, it will become natural log, absolute value of -1, plus a constant. So I threw the -1 inside here, then go minus, throw -2 inside there, natural log of -2, plus a constant. Then when you distribute this negative sign across, the constant just cancels out. You're just going to get natural log of 1 after completing the absolute value here. This constant is gone, minus natural log of 2. The whole thing just turns into natural log 2. So that would be the answer on this thing, whether we put a constant on it or not. Here, this notes look a little bit weird. Let me put here just a sidebar. And let's say this is the reason we don't need a constant C. And here we can say it cancels. So even if you put in the world's fanciest constant inside your antiderivative, it wouldn't even make any difference on these kinds of problems. Let me put a little border here. And don't forget, this antiderivative is very important. Whenever we do an antiderivative of 1 over x, don't forget the absolute values. That's the easiest thing to miss on this kind of thing. Now back to this problem. I guess we've kind of solved it, but let's run through it anyways. Throw in -1 inside natural log x. Go minus, then take natural log of lower limit of integration, -2. Kind of a lazy, oh, I did make a mistake. That should be an absolute value. Then this turns into natural log 1, becoming a 0, minus natural log of 2. And the whole answer is negative natural log of 2. Now notice this time we got a purely negative answer. That suggests that the function 1 over x is below the x-axis. And that makes sense because we're only putting in negative numbers inside the domain, from the domain inside this function. So it does purely live below the x-axis, and we really should be getting a negative quantity. But that's an interesting antiderivative there. Before we see other ones, that's one that we definitely have to mention. And this is something that will come up quite a bit as well in the homework. Missing the absolute value sometimes doesn't make a big deal, but in this kind of problem, it's absolutely important. We can't get a value out without it. Well, any other questions, folks, on this part C here? Okay, let's try then slightly harder problems. They can't get too hard, but they definitely get tricky in a certain sense. The next one we should take a look at is, I believe this is part D, is a definite integral from 1 to 2. The function is going to be 5x plus 1 multiplying x minus 1 dx. So that's our function we would like to take care of or integrate right here. But there's a big problem with this kind of thing. I don't necessarily know the antiderivative of a function times a function in this format. In fact, if we were to even differentiate that, I would not differentiate it as it stands. That would involve the product rule, right? And the product rule isn't necessary for this problem. Way faster to just expand it and then differentiate term by term. And it's the same with antiderivatives. The antiderivative of 5x plus 1 times the antiderivative of x minus 1 is not the antiderivative of this whole integrand right here. We really have to expand all this, get it to several terms, and integrate term by term. So always be careful or suspicious if you see functions multiplying or dividing. It probably can't be done in the way we think it would be. Let's start off by going like this. Integrate from 1 to 2. Let's expand out. 5x multiplies through, giving 5x squared minus 5x plus x minus 1. Parentheses this time are just to emphasize everything there is contained inside the integral, but that should be clear because of the dx and the integral sign. Let's combine our like terms. Now it's integral from 1 to 2, a 5x squared minus 4x minus 1 dx. And honestly, this step is a step that's easy to miss too. If you didn't simplify your function in here, you're doing a lot of additional work. Definitely simplify your functions before you differentiate and before you integrate, and it's always much, much easier. So now all we need is an antiderivative of that thing right there. We'll go term by term because they're not being multiplied. We can do this in the ordinary way. So on the 5x squared, this will turn into 5x to the new power of 3, so divide by 3. If you differentiate that, 3 comes down and it's just 5x squared, making it the right quantity here. On this one, we know the new power is going to be 2, and we'll divide 4 by that new power. So let's write in minus 2x squared. Then park your eyes here, eyeball it a minute, differentiate it mentally. That'd be negative 4x, which matches up. So we're definitely on the right track. The next one, for -1, because it's a constant, we'll just throw in negative x. Then this whole thing is evaluated from 1 to 2. Our hopes is that there'd be a 0 there, but it doesn't have to be. There's just a little bit extra work to calculate this now. So let's go and write this in as 5/3. Where x was, would we put in the 2 or the 1? Any volunteers for what should go here? Exactly. We always start on the upper limit first. Plug that into your antiderivative in the parentheses. So 2 here first, minus 2 by 2 squared. And then side here, minus 2. Then we would switch to the lower limit of integration, but we have to be careful with this function because it comes in as 3 terms. Definitely include a parenthesis around it so we can make sure we distribute that negative sign appropriately. We're plugging in a 1, so this one's not too bad. It'll just be 5/3. Minus 2, minus 1. So now that's our problem to calculate. And this is a good time to pause here for just a moment. When you're doing these as a homework question, the steps that we have to take are definitely show the antiderivative. So that's definitely part of the calculus. We also have to show the evaluation. Show the evaluations. By that, we mean plugging 2 in and 1 in and subtracting. But beyond that, it's really kind of up to you. If you like fractions, doing arithmetic by hand, it's always good practice, honestly. If you have the time, it's worth doing. But if you're a little bit rushed on time, I don't mind if you take what's purely arithmetic and throw it into a calculator. I'll leave it up to the class today. Should we do it by hand or put it inside Desmos? Let's do it by hand. Good call. So by hand, we can first take 5/3 here. 2 cubed will give us an 8. Here we have 2 times 2 times 2, so really just minus 8. Then minus 2. Here this is going to distribute to give us a negative 5/3. Let me do a couple steps at once. This will combine as a -3, multiply by the -1, so now +3. And now we've got some fractional parts, some integer parts. Here we have 40/3 minus 5/3. Then here to here is minus 10 plus 3 looks like a -7. So now here to here takes us to 35/3 minus 7. But we can make that 7/1, multiply by 3/3. And this is 35/3 minus 21/3, coming out as 14/3 altogether. That's definitely an adventure. And after you calculate something like this, in your homework, it might not be a bad idea to definitely take advantage of some technology. It's available right now. It's not available on exams, so this is our chance to get some extra insight on the problem and see if it's even reasonable. I got a purely positive answer, so let's see if that makes sense in the problem. Let's put in that original integrand inside the graphing calculator. It's 5x plus 1, x minus 1. It also needs a domain. It's going from 1 to 2. So our curly brace, 1 less than x less than 2, puts in the right domain. Let's take a look at that. That's our function. It's not the world's most amazing function, but there's definitely positive area under here. And what we just showed is that the direct and exact area under this curve is the 14/3. So that's kind of interesting in a way. I would have never guessed that, but now we can do this kind of stuff exactly. And for the problem that was mentioned earlier of actually evaluating the limit using the summations of different powers, let me get rid of that last line. This is the kind of problem that the author did do in section 5.2, but by first principles, only using the limits of Riemann sums and actually evaluating that limit. That is a fantastically hard kind of problem, and lots of special formulas get involved. But if you're using the fundamental theorem of calculus, this is all it is. Antiderivative evaluated in two places gives us that answer directly. So it's kind of rare that a theorem this powerful can save that many steps, but that's always the value of a good theorem. It makes computation much more approachable. Well, we're at our last 2 minutes, so we won't be able to do any more right here. But my plan for when we come back on Monday's class is I want to come back to these notes because I feel like this strategy of integrating just definitely requires more practice. Doing just 4 problems, I don't feel like is good enough. We'll do several more just to get some extra practice on this. But any last questions then, folks, before we call it a night? Yeah.
So on that last part, could we use the insert of decimal or the emphasis of the fraction?
If you give me the exact decimal, I'd be totally fine with that. So yeah, if you go to Desmos and go 14/3 and read it out as 4.6 bar, I'd say that's a completely appropriate answer as well. Thanks, you too. Hello. Just turning off this live stream real quick.